3.6 megapascals. That is the amount of stress a new model says is now loaded onto a single segment of the San Jacinto Fault northeast of Los Angeles, the highest value that model found anywhere in 1,000 years of reconstructed earthquake history. But the number itself is not what has researchers concerned. It is what is sitting next to it. The San Andreas segment alongside it is loaded to nearly the same level, and that specific pairing is the condition that has historically preceded the worst kind of California earthquake. About 50 miles northeast of downtown Los Angeles, Interstate 15 climbs out of the basin through a gap in the mountains called Cajon Pass. Roughly 100,000 vehicles a day move through it. Underneath that highway, and underneath the rail lines and the gas lines and the power transmission corridors that share the same gap, two of the most dangerous fault systems in North America come within a few miles of one another. The San Andreas runs across the pass. The San Jacinto runs up to meet it from the southeast. And a team of researchers has now spent 1,000 simulated years watching what happens at the place where they nearly touch. The paper is titled Cajon Pass and the Southern San Andreas Fault System, Earthquake Cycle, Stress Accumulation, and Present-Day Loading. It was published in the Journal of Geophysical Research, Solid Earth. The lead author is Dr. Lilian Burkhardt of the University of Bern in Switzerland, working with colleagues at the University of Hawaii at Manoa, the United States Geological Survey Earthquake Science Center in Pasadena, and the Scripps Institution of Oceanography at the University of California, San Diego. The headline that traveled around the world was a number. Tectonic stress in Southern California, the model found, has reached and in places exceeded the highest levels of the past 1,000 years. That number is real, and it is worth taking seriously. But it is not the most important thing in the paper, and treating it as the story has meant that the actual finding has gone largely unreported. The actual finding is about a junction, and about the difference between a bad earthquake and a categorically worse one. The researchers introduce a concept they call an earthquake gate. A gate is not a wall and it is not a funnel. It is a junction between fault systems whose behavior is not fixed. It responds to conditions that change over centuries, and it decides whether a rupture that starts on one fault stays on that fault or crosses onto the other one. That distinction is the entire story because of how earthquake magnitude works. The size of an earthquake is governed principally by the area of fault that breaks. A rupture confined to one system produces one length of torn crust and one magnitude. A rupture that crosses a junction concatenates two systems into a single event, and the magnitude climbs accordingly. In this specific case, the difference between a closed gate and an open gate is the difference between a severe regional earthquake and one that sweeps across greater Los Angeles, San Bernardino, Riverside, and the Coachella Valley in the same shaking. Southern California has already run this experiment twice, and it produced both answers. On the 8th of December, 1812, an earthquake now estimated at magnitude 7.5 struck the region near what is today Wrightwood. It did not stay on one fault. The rupture propagated through the Cajon Pass junction and across both fault systems in a single through-going event. The gate was open, and the earthquake used it. That event is the historical proof that the junction is capable of transmitting a rupture. It is also, and this matters for the rest of this story, the one of the two examples whose exact extent is least well constrained. The researchers had to choose between competing published interpretations of how far the 1812 rupture actually reached, and they chose one. The 1812 earthquake is remembered in California mostly for what it did to the mission churches. It brought down the bell tower at San Juan Capistrano during morning services and killed dozens of people inside, and it is often called the Wrightwood event because paleoseismic trenching in that area eventually tied the rupture to the San Andreas. But the reconstruction of where the fault actually broke, and how far, has been argued over for decades. One published interpretation has it crossing onto the San Jacinto. Another argues for a different geometry entirely. Separate geological work published in the journal Geology has since presented physical evidence for joint ruptures of the two systems, which strengthens the case that this junction really does transmit earthquakes rather than merely appearing to. The researchers built their model on the crossing interpretation, and it is fair to say the model would look different if they had chosen otherwise. 45 years later, on the 9th of January, 1857, the southern San Andreas produced the largest earthquake in California's written record. The Fort Tejon earthquake registered at approximately magnitude 7.9 and left a surface scar roughly 220 miles long. It was an enormous rupture by any standard, and it stopped at Cajon Pass. It did not involve the San Jacinto fault at all. The gate was closed, and an earthquake with more than enough energy to keep going simply ran out of road at the junction. The extent of the 1857 rupture is well documented, which makes it the cleaner of the two examples. Accounts from the time describe the Kern River running backward and trees snapped along the fault trace, and the offset is still visible in the ground today in places where a stream channel was carried sideways and never straightened out. Only 2 people are known to have died, for the simple reason that almost nobody lived along the 220 miles that broke. 2 great earthquakes, 45 years apart, arriving at the same junction and getting opposite answers. The question the researchers set out to answer is what made the difference, and the answer they landed on is not about the earthquakes at all. It is about the state the junction happened to be in when each one arrived. Their answer required building something more elaborate than a map. The team constructed what is called a 4-dimensional earthquake cycle model, 3 dimensions of space plus time. It tracks how each earthquake in the record changed the stress on its neighboring fault segments, how stress rebuilt during the quiet intervals in between, and how the hotter, more pliable rock beneath the brittle upper crust slowly relaxes for years and decades after a large rupture. That last piece is why the model needs a 4th dimension. The crust does not finish adjusting when the shaking stops. It keeps flowing and settling underneath, and every one of those adjustments quietly changes the stress state at the junction long after the earthquake has left the news. Into that model, the researchers fed a 1,000-year earthquake record reconstructed from geological evidence. Some of it comes from radiocarbon dating of disturbed sediment layers exposed in trenches dug across the faults. Some of it comes from tree ring anomalies, where a growth record registers the year the ground moved. Some of it comes from historical documentation of ground ruptures. They combine that history with United States Geological Survey fault slip rates and locking depths, and with the physics of how stress transfers between neighboring faults. The trenching work deserves a sentence of its own because it is where most of this record comes from, and it is genuinely unglamorous. Researchers cut a trench across the fault, often in a place where a marsh or a stream has been quietly laying down sediment for centuries, and then they read the wall of that trench like a stack of pages. Layers sit flat until an earthquake breaks them. The break gets buried by the next few centuries of sediment, and then the next earthquake breaks that. Organic material in each layer can be radiocarbon dated, which brackets when the ground moved. Do that at enough sites along a fault, and you have a rupture history that reaches back well past anything written down. That transfer mechanism is worth one moment of explanation because it is the reason a 1,000-year reconstruction is necessary at all. Faults do not fail because time passes. They fail when the force pushing the two sides past each other overcomes the friction and the clamping pressure holding them locked. Engineers and seismologists fold those effects into a single quantity called Coulomb stress. A positive change pushes a fault closer to failure. A negative change pushes it further away. And when an earthquake happens, it does not just relieve stress on itself. It redistributes stress across every fault in the neighborhood, loading some of them and unloading others. Which means the stress sitting on the San Jacinto fault this morning is partly the inheritance of what the San Andreas did in 1812 and again in 1857. You cannot understand the present state of this junction without running the whole millennium. 3 fault sections converge at Cajon Pass. 2 of them belong to the San Andreas, the segment called Mojave South and the segment called North San Bernardino. The third belongs to the San Jacinto, and it is called San Jacinto Bernardino. All 3 have accumulated high Coulomb stress in the model. That convergence, all 3 loaded at once, is the single most notable result in the paper. The specific numbers are these. Modeled present-day stress on the San Jacinto Bernardino section stands at 3.6 megapascals. That is the highest value anywhere in the entire 1,000-year reconstruction, and it exceeds that same segment's previous peak from nearly 50 years ago. On the neighboring Mojave South section of the San Andreas, the figure is 2.8 megapascals. A megapascal is not an intuitive unit, so it is worth anchoring. 1 megapascal is roughly 10 times atmospheric pressure at sea level. 3.6 megapascals sounds almost trivial compared to the enormous confining pressure of rock at fault depth, which runs into the hundreds of megapascals. But that is not the comparison that matters. What matters is the amount of stress a fault typically sheds when it finally breaks, which for a large continental strike-slip earthquake lands in the range of a few megapascals. In other words, the excess stress the model has accumulated on the San Jacinto Bernardino segment is roughly the size of a full earthquake's worth of release. The bank account is not just full, it is full to the exact figure the withdrawal usually is. Now here is the part that changes what those numbers mean. The researchers found that the decisive factor at the junction is not how much stress has built up on either fault taken alone. It is how aligned the stresses on the two systems are with each other. When stress on both faults rises in concert over time towards similarly high levels, the conditions favor a large joint rupture that crosses both systems. When the two evolve out of step, One loaded, one recently relieved, ruptures are far more likely to terminate at the junction and go no further. The gate closes not because it is strong, but because the fault on the other side is not ready to receive what is being handed to it. 3.6 megapascals and 2.8 megapascals are both high, and they are relatively similar. That is the configuration. In Burkhard's own words from the university's release, so not only is it concerning that the stresses are reaching historic highs, but also that the relative stress conditions between the two fault systems are approaching the range we associate with major ruptures, crossing both faults simultaneously. And that is a scenario with much larger consequences for the region. A joint rupture crossing Cajon Pass has been characterized in coverage of the study as potentially approaching magnitude 7.4 to 7.8. That range sounds modest next to the 7.9 of Fort Tejon until you look at where the shaking would land. Fort Tejon tore through country that in 1857 was almost entirely empty. A through-going rupture at Cajon Pass in 2026 would put its energy directly into the corridors where roughly 20 million people live and work. And that is where the honest reporting on this study has to slow down, because the model that produced those numbers had to assume some things in order to produce them at all. An independent commentary on the paper was published by Ross Stein of Temblor at the end of June, and reviewed by Burkhard herself before publication. It is unusually useful because it neither dismisses the work nor inflates it. Stein calls the paper comprehensive and very well reasoned. Then he identifies the two assumptions that govern the outcome. The first assumption concerns the prehistoric earthquake record. The model takes as given that the dates of past earthquakes inferred from trench excavations are essentially correct, which is a reasonably solid assumption, and also that the rupture extents and magnitudes inferred from those dates are correct, which is a great deal less certain. Here is why. A trench dug across a fault tells you very well when the ground moved at that one spot. It tells you much less about how far the rupture traveled in either direction. To estimate a magnitude, researchers have to correlate earthquake horizons between isolated trench sites spread along hundreds of miles of fault and decide which ones represent the same event, a process sometimes called stringing pearls. Published work has raised the possibility that this approach may inadvertently overestimate how frequently large ruptures occur. If the prehistoric earthquakes were smaller than assumed, the modeled stress history bends. The second assumption is about what an earthquake does to the stress it releases. The model assumes each rupture fully discharges all the accumulated stress on the segment that broke, after which loading restarts from zero. This is a long-standing framework known as the slip predictable model, and there is now considerable evidence that neither it nor its main alternative matches how real faults actually behave, partly because faults interact, and almost none of them are isolated. The authors state the consequences of that choice plainly, which is the correct scientific practice, but the assumption still shapes the answer. The geometry gets simplified too. These faults are visibly splintered where they reach the surface, and the best evidence suggests they are just as tangled at depth. Southeast of the pass, the San Andreas splits into two separate strands before rejoining farther south. Cajon Pass is also only one of many junctions in Southern California, not a uniquely important bottleneck. All of that complexity, the splays, the branch faults, the strands, has to be smoothed into something a model can actually solve. There is also a caution buried inside the model's own output. Between 1329 and 1469, the reconstruction shows an interval of roughly 140 years in which stress climbed and no large earthquake arrived. The intervals between events in this record follow no schedule whatsoever. As Stein puts it, we cannot talk about faults being 10 months pregnant. The gestation periods are wildly variable. Something else is worth noticing, and it cuts against the instinct to read every tremor as a countdown. In the month spanning late May through late June of this year, there was no concentration of earthquakes at or near Cajon Pass. None. The stress at the junction is modeled. The quiet at the junction is observed. That is not reassurance, and it is not a warning. It is simply what a locked fault looks like. A fault, storing energy for a great earthquake, does not chatter about it beforehand. Silence is the mechanism, not the absence of one. There is a related puzzle in the same region that nobody has solved. The San Andreas, northwest of Cajon Pass, slips at roughly twice the rate of the San Jacinto to the southeast. Yet the San Jacinto produces about 10 times more small earthquakes. Two comparable faults, running in parallel, behaving in completely different ways at the small end of the scale. No one fully understands why, and that gap in understanding sits directly underneath any attempt to read the junction's mood from a seismograph. Zoom out, and the pattern gets easier to see. It has been 169 years since the Fort Tejon rupture, and 214 years since Wrightwood. For comparison, it has been 120 years since the 1906 San Francisco earthquake and 158 years since the 1868 Hayward event. Southern California has waited longer than Northern California, and the wait grows longer still on the segments southeast of the pass. Meanwhile, California's damaging modern earthquakes have all happened somewhere else. 1933 at Long Beach, which rewrote the state's school building codes. 1971 at San Fernando. 1994 at Northridge, which killed 57 people and caused up to $40 billion in damage. The Ridgecrest sequence in 2019, not one of them was the southern San Andreas. The same logic runs north, where the Cascadia subduction zone has been locked and largely silent since it last ruptured in January of 1700. On this coast, a quiet fault is not a safe fault. Quiet is how the stress accumulates. The other reason this particular junction earns a 1,000-year model is what physically occupies it. Cajon Pass is a choke point. Interstate 15 runs through it, carrying the freight and traffic connecting the Los Angeles basin to Las Vegas and the interior west. Mainline rail runs through it. High-pressure natural gas lines run through it. High-voltage electrical transmission runs through it. Fiber optic trunk lines run through it. Water conduits supplying greater Los Angeles run through it. The reason all of that is stacked into one narrow gap is the same reason the gap exists. The mountains on either side were pushed up by the faults, and the pass is the low spot the faults themselves created. Every engineer who has ever needed to get something from the basin to the interior has looked at the map and made the same decision, which is why more than a century of infrastructure has been laid down along the one line you would least want to build on if you had a choice. The gap in the mountains that decides how big the earthquake gets is the same gap that everything in the basin depends on afterward. A through-going rupture would damage the corridor and the cities it serves in the same instant. The road you would need to bring aid in on is built on top of the fault junction that let the rupture through. That is not a hypothetical vulnerability. It is a design feature of Southern California, inherited from geography, and no amount of modeling changes it. That is the practical case for the study existing, and it is the case Burkhardt herself makes. The stated purpose of the work is hazard assessment, infrastructure planning, and emergency preparedness, not forecasting. She has also built a public tool called LA Grid that visualizes seismicity and fault data for the Los Angeles region with live updates, precisely so that the information does not stay locked inside a journal. So where does this leave anyone actually living in Southern California? The defensible version of the finding is this. The southern San Andreas system is heavily loaded, which decades of prior work already indicated. What is new is a physically grounded explanation for why Cajon Pass sometimes allows a rupture to cross and sometimes stops it, and a model showing that the two systems meeting at the junction are currently loaded to similar, historically high levels, which is the state that has preceded crossings in the reconstructed past. The version that is not defensible is a countdown. The study contains no timing information, and neither Burkhardt nor any independent reviewer has pointed to data suggesting an imminent rupture. Today's elevated stress could sit there for another several decades. It could also release tomorrow. Both of those sentences are consistent with everything in the paper, and anyone telling you otherwise is adding something the science does not contain. What is worth watching is not a seismograph. It is whether this framework gets applied, whether hazard maps and building standards and lifeline planning for the Cajon corridor start treating a joint two-fault rupture as a scenario to design against rather than an outlier. The researchers explicitly built the method to be portable to other complex fault junctions worldwide, so the same question will eventually be asked of junctions well outside California. And the practical answer, for anyone in the region, has not changed with this paper, which is somewhat the point. Secured water, a plan for the days when the corridor is closed, a retrofitted foundation if the building predates the codes that came out of the last disaster. Ross Stein's closing line on the study is the one to keep. There is no reason for alarm, but there is an acute need to be prepared. The gate has been opened before. It has been closed before. The new work tells us which way it is leaning right now. And the honest thing to say is that leaning is not the same as swinging.